Hi, today we're going to discuss a very important topic called Riemann sums. So, to this point in calculus, you've been worrying about derivatives and slopes of tangent lines, and Riemann sums are really where we start to get into the second half of the course, and we start to talk about areas under a curve. So, if you have a graph on an xy axis, let's say that y equals the square root of x. So you have a graph like this. And we're asked to find this area underneath of the curve. Now, if the graph was a circle or a rectangle, that would be easy. We just use our geometry and calculate the area. But it's not. Y equals the square root of x. There's no area formula for that. So what do? Well, that's where Riemann sums come into play. What we can do is estimate the area by breaking it up into a group of rectangles. So, for example, we take our graph and we break it up into 3 rectangles. If we can calculate the area of each of these rectangles, we can get the area under the curve and approximate it. So, how do we go about doing that? Well, let's call the end of this rectangle x sub 1. Let's call the start x sub 0, x sub 2, x sub 3, and so on. Alright, so the area of a rectangle is the width times the height. So, the area total is just going to be the sum of all those rectangles. So the first rectangle is going to be f of x sub 0. That's the height of this function, called f of x. The height of the function at x equals 0, that's this point here, times the width of this interval, which is simply x sub 1 minus x sub 0. Now, we add up all the rectangles. So, our next term, plus f x sub 1 times x sub 2 minus x sub 1. And our third rectangle, f x sub 2 times x sub 3 minus x sub 2. So all we've done is broken it up rectangle by rectangle, and we're adding all those areas together. The notation looks complicated, but the concept is very simple. Now, one more note about this graph. This is called a left-hand Riemann sum. We call it left-hand because we use this left endpoint for the height of the graph. We can also do a right-hand Riemann sum. So let's look at what that would look like. So let's use the same graph, y equals square root of x. Alright, so if it's going to be a right-hand sum, we're going to use the right endpoint of each rectangle. Okay, so if we can estimate the area of all these rectangles, we can get the area under the curve. And let's label our x's one more time. So we'll start at x sub 0, move to x sub 1, x sub 2, and so on. So let's just go through the same process. Let's add up the area of those rectangles and see if we can find a pattern so that we can simplify our notation a little bit. So first of all, we would have f x of 1 times x sub 1 minus x sub 0. Those are our areas. That's our first term. Then we would have f x sub 2 x sub 2 minus x sub 1. That's our second term. Go ahead and write the third term too, so that we can see a pattern. Fx sub 3 times x sub 3 minus x sub 2. So, alright, so now we can do this, and if we look at it really closely, notice how we start with f of x sub 1, we go to f of x sub 2, then to f of x sub 3. So if we're going to simplify this and write it in summation notation, we can write the sum from k equals 1 to n, where n is simply our number of rectangles that we want under the curve. The more rectangles we have, the more accurate our approximation of the area will be. So we start with that, and the next piece of our notation is the height of the rectangle. So that would be f x sub n, and then the width of the interval is simply going to be x sub n minus x sub n minus 1. So this is something of a typical form that we would see for a Riemann sum. Alright, so when we add all these rectangles under a curve, we are just approximating the area. We want to do better than approximating. Well, we find that the more rectangles we have, the better approximation we get. Take a look here. Here we have 6 rectangles, and we do miss some space under the curve in these places. However, we don't miss nearly as much space as if we just had 3 rectangles. So, if we could develop a system where we have an infinite number of rectangles, we would no longer be approximating the area, we would have a definite amount. We'd be certain about it. So, how are we going to go about doing that? Well, suppose we have a function, f of x. So, all we need to do is add up rectangles with their heights and their widths. Well, typically in a Riemann sum, the width of the rectangles is constant throughout. Each rectangle is the same width. So we call that delta x. That delta x is simply going to be the total interval, we'll call it b to a. Dang it, man. That delta x is going to be over an interval. Let's call that interval a to b. And all that delta x is going to be is an equal width, depending on the number of rectangles we have, over this interval a to b. So we can call delta x b minus a over n, where n is the number of our rectangles. So, all we need to do to have infinite rectangles is to take the limit as n goes to infinity. So we have the limit as n goes to infinity of our sum from k equals 1 up to n of our function f of x sub k times the width of each rectangle, which we just said is delta x. So, that is the answer. That is the area. Can we really sit down and calculate it? Well, we don't really want to add up an infinite number of terms. However, the concept of this carries through more and more to calculus. Now, before we wrap things up, you'll see this sum written in many different ways. So, notice that this term, x sub k, that's the x you choose for a given rectangle. All this equals is going to be our starting point of the interval, a, plus a constant times our delta x. So that will let us rewrite our sum in a different form. We can now write that the area equals the limit as n goes to infinity of sum sum from k equals 1 to n of f of a plus k delta x times delta x. All we did is replace our x sub k with this term here. Likewise, we can replace delta x with b minus a over n, and you can see that sum written as such. So, these two sums and the sum we saw before, they're all equivalent, it's just different notation. Okay, so let's take a minute to take what we've learned about Riemann sums and let's plug in a concrete function. So let's say that f of x equals sine of x. And we want to know the area under that curve from 1 to 2. So visually, if we draw our sine curve, we want to know essentially that area. So how are we going to do it? Well, let's write an infinite sum. So the area is going to equal the limit as n goes to infinity of the sum from k equals 1 to n of f. Let's use this form of the Riemann sum where we replaced x sub k and we replaced delta x. So this would be a plus k delta x times delta x. Well, if you remember, delta x is simply b minus a over n, which in this case would be 2 minus 1 over n, or just 1 over n. Alright, so if we try and take sine of x and write it in a Riemann sum, it's going to look something like this. So forward. Alright, so our area would equal the limit as n goes to infinity of the sum from k equals 1 up to n of sine. A is just 1, that's the start of our interval, plus k times 1 over n. So that's this term. Our second term, delta x, which we just wrote, is simply 1 over n. So this here would be our Riemann sum, and that is how we can calculate the area under a sine curve. Now, like I said before, are we really going to add up an infinite amount of rectangles? No. But this discovery led Newton to develop something called integrals, which you'll learn about later with the fundamental theorem of calculus.